So in this video, we're going to continue looking at chemical reactions and how they obey the law of conservation of mass. And we're going to do so by what we call balancing equations. But before we get to that, we need to take a look at some of our symbols and the meanings of those symbols in a chemical equation. So an arrow means produces or forms. A plus sign is just exactly what you think it is, plus or and. An S stands for our state of matter solid. An L stands for the state of matter liquid. A G stands for the state of matter gas. And now we've already discussed solid, liquid, and gases in a previous unit. Now here's a new one, AQ. AQ means aqueous. And aqueous simply, and that's an O-U-S. Let me make that look a little neater. All right, and aqueous simply means a substance that has been dissolved in water. So when I dissolve something in water, I now have a solution that I call aqueous. A triangle over the line means heat has been added. So this is a reaction that does not work unless we apply heat to it. All right, and we're going to see these symbols throughout this unit. All right, so a chemical equation. 1 unit of aqueous lead 2 nitrate plus 2 units of aqueous potassium iodide produce 1 unit of solid lead 2 iodide and 2 units of aqueous potassium nitrate. So we've got a word equation. We can put this into its chemical equation using our symbols, all right? And we're going to balance it by using coefficients, which is the number of units in each substance. Now, these units actually have a name. And when you get to chemistry next year, then you're going to learn a little bit more in depth about what this coefficient actually means and the name of it. We call it the number of moles within a reaction, and you're going to kind of dive into that in a lot more detail next year, all right, when you take chemistry. But for right now, we're just going to call them units because that's really all we need to know for this class. All right, so the coefficient is the number in front. So I had 1 unit of aqueous lead 2 nitrate. There's an understood 1. So if there is no coefficient in front, just like in math, x is understood to be 1x, this is understood to be 1 unit. So I'm just going to go ahead and plug in that 1 for a visual for you. Notice I said it's aqueous, so this has been dissolved in water, plus 2 units of aqueous potassium iodide. So here's the 2. So here are my 2 coefficients in the reactant side. All right. Produces, so produces is my arrow. 1 unit of solid lead 2 iodide. So I have an S for solid. And again, there's no 1 in front. I'm going to put the 1 as a visual for you, but we don't normally add it. It's understood to be there. And 2 units of aqueous potassium nitrate. So AQ for aqueous, and here's my 2. So my coefficients for the products are the 1 and that 2. Now, where did these 1s and these 2s come from? And they came from balancing equations in order to obey the law of conservation of mass. So we are going to use coefficients so that the number of atoms are equal on both sides. All right, so let's look at our equation up here real quick, and let's count. We have lead and I have this polyatomic ion NO3 nitrate. The coefficient goes to the entire equation. Anything times 1 is 1. So how many leads do I have? I have 1 lead as a reactant. Now my nitrate is parentheses. I have a 2 behind it, so how many nitrates do I have? 2. I have a 2 in front of the K and the I. So how many potassiums do I have in just the Ki? And that is 1. This 2 is going to be multiplied. So if I start with 1 potassium, 1 times 2 is 2. So I have 2 potassiums. I have 1 iodine as well to start with in Ki. 2 times 1 is 2. Now, let's look at the product side. I have 1 lead because anything times 1 is 1. So guess what? I had 1 in the reactant and I have 1 in the product. I have 2 iodines and 2 times 1 is 2. There we go. I had 2 iodines in the reactant. I'm going to put a parenthesis around my NO3 just to give you a visual of that polyatomic ion. K. I have 1 potassium to begin with. All right, 1 potassium to begin with here. And 1 times 2 is 2. I have 2 potassiums. I have 1 nitrate to begin with. And 1 times 2 is 2. So my reactants equaled my products. So the law of conservation of mass has been fulfilled. So let's look here. How are we going to balance? We are going to balance left to right. We are going to save hydrogen and oxygen for last. We are going to balance polyatomic ions, and I'm just going to write Pi for polyatomic ion as a unit if possible. And our final rule, most important rule, so I'm going to star it, and I'm going to put it in all caps. Check your work. All right, so let's start left to right. I have 1 aluminum on the left. I have 1 aluminum on the right. So my aluminums are balanced. I have 1 copper on the left as a reactant, and I have 1 copper on the right as a product, so those balance. I have 2 chlorines on the left, and I have 3 chlorines on the right. Because everything is balanced except for chlorine, I can put a 1.5 in front of here, because 1.5 times 2 is 3. I have 3 chlorines on the left. I have 1.5 on the right. Now, we cannot have a half of a compound. So in this case, I have to multiply everything by 2. So 1 times 2 is 2. 1.5 times 2 is 3. 1 times 2 is 2. And 1 times 2 is 2. Now, we're going to check our work. I have 2 aluminums. I have 3 coppers. I have 2 coppers. Uh-oh, I need 3, so we're going to fix that and make it a 3. 2 chlorines times 3 is 6. 2 times 3 is 6. And chlorine over here has 3. 3 times 2 is 6, so that works out. Now, that way is a little bit more tricky because as you saw, our coppers didn't match up. So that's not necessarily it works, and that will work for you. But let me show you another way to do this, which you may find to be easier, okay? We've already determined that our aluminums are the same and our coppers are the same. Our chlorines are the only thing that need to balance. So if I have 2 chlorines on the left, or 3 on the right, what is the common denominator? 2 times 3 is 6. So if I need 6 chlorines, 2 times what is 6? 3. 2 times 3 is 6. And if I have 3 chlorines on the right, what times 3 is 6? 2. Now we just go back. My aluminum has 1 aluminum. 1 times 2 is 2. And my copper has 1 copper here. 1 times 3 is 3. So that way I think is actually a little easier, but I wanted to show you both. If a polyatomic ion is present, you're going to balance it as the polyatomic ion. So NO3, I'm going to go ahead and just put that in a parentheses to give us a visual. Here we go. I have 1 magnesium on the left, and I have 1 magnesium on the right. I have 1 silver on the left. I have 1 on the right. Now my polyatomic ion is in a parentheses. There's no number behind it, so it's understood to be 1. My polyatomic ion on the right side has a 2 behind the parentheses, so I have 2 nitrates. So I need 2 nitrates as reactants. All right, so 1 nitrate times 2 is 2. Now, when I put this in front of my silver nitrate, my silver, which was balanced, is no longer balanced. I started with 1 silver. 1 times 2 is 2. So how many silvers do I have over here? 2. 1 times 2 is 2. And finally, let's check our work. I have 1 magnesium on the left and 1 on the right. I started with 1 silver. 1 times 2 is 2. I have 2 silvers on the right. 1 times 2 is 2. My nitrate is in parentheses. There's 1 of them. 1 times 2 is 2. And on the product side, my nitrate is in parentheses with the 2 behind it. All right, there's a 1 in front. So this also has 2 nitrate.